Now let's talk about properties of logarithms. So first of all, we're going to define a logarithm. The statement y equals log base a of x is equivalent to saying a raised to the yth power is equal to what's inside the log, the x. So you want to remember this definition going back and forth between the exponential and the logarithmic statement, because this is what we're going to use to evaluate or rewrite certain logarithms, is being able to take a statement like this and translate it into this form, or equivalently, we can solve an exponential by taking a statement like this and translating it into this form. Now, the a here and here is the base, the y is the exponent, and the x is the number that we're working with, the argument of the log. Now notice that I said y is the exponent, and this says y equals the logarithm. That means the logarithm is an exponent. It's the exponent you must raise a to in order to generate x. For example, 2 cubed is 8, so log base 2 of 8 equals 3. It's the base 2 to the exponent 3, 2 to the third, equals what's inside the log. Since 1/2 to the negative fourth is 16, we would say log base 1/2 of 16 equals the exponent negative 4. 5 to the first is 5, so log base 5 of 5 is 1. The exponent is the 1. 3/4 to the 0th power is 1, so log base 3/4, the base is the same, log base 3/4 of 1 equals the exponent 0. All right, so let's use this to solve a few problems. Log base 16 of 4 equals x is equivalent to saying the base raised to the power. So 4 equals, right, 16 to the xth power. Our base to the exponent equals what's inside the log. Okay, so this is saying what power do I have to raise 16 to make it a 4? Well, I have to take the square root of 16 to be a 4. Square root as an exponent is a half. Now let's do this one. The base here is the x, so x to the third equals 125. So if I'm trying to solve this now for x, I would cube root both sides. Cube root of 125 is 5. Okay, base to the exponent equals what's inside the log. So what's inside the log is the base 32 to the exponent negative 1/5. All right, well that's the same as saying 1 over 32 to the 1/5 power, because the negative exponent means put it in the denominator of a fraction. X equals 1 over, that's the 5th root of 32 when I have a 1/5 exponent. And the 5th root of 32 is 2. For all positive numbers x, if I write log without a base on it, it's understood to be log base 10. So this is saying log base 10 of 12 equals, well, to figure that out, I can plug that directly into my calculator. If I do, I'll get about 0.079. Log of 0.1, now again, this is log base 10, so I can treat this like this is saying log base 10 of 0.1 equals x, then I would say that understood 10 down here to the x power equals 0.1, or 10 to the x equals 1.1 is 1/10. So that means that this is 10 to the negative 1, so the x must be a negative 1. And again, you can find that by plugging it into your calculator as well. And then log of 3/5 is log base 10 3/5. Plug it in. Let's look at that one. So if I pull out my calculator, My log key is right here. So log of 3 divided by 5 would be about negative 0.2218, and so on. In chemistry, the pH of a solution is defined as pH equals negative log of, okay, now this is our H3, 3 hydrogens, 1 oxygen, right? So where this is the hydronium ion concentration in moles per liter. The pH value is a measure of acidity or alkalinity of a solution. Pure water has a pH of 7. Substances with pH values greater than 7 are alkaline, and less than 7 are acidic. Let's find the pH of a solution with our ion concentration as being 2.5 times 10 to the negative 4 and classify it as acidic or alkaline. Then let's find the hydronium ion concentration of a solution with pH equals 7.1. All right, so looking at this first one, if this is the value, we replace that inside the log in our formula. So the pH would equal negative log of 2.5 times 10 to the negative 4. Again, we can plug that directly into our calculator and get 3.6. The way I'd plug that in is I'd say negative log of, I can either type 2.5 times 10 to the negative 4, or I could equivalently translate 2.5 times 10 to the negative 4 as a decimal first, and then plug it into the log. Now let's look at the second one. I want to find the hydronium ion concentration of a solution with a pH of 7.1. So notice in my formula, the pH is the 7.1, so the 7.1 goes on this side of the equation. So we would say 7.1 equals negative log. Okay, now to get out of this statement, remember this is a log base 10, so I'm going to say 10 raised to the exponent 7.1 equals what's inside the log. Well, first we move the negative over. So 10 to the negative 7.1 equals what's inside the log. All right, so again, I can plug this directly into my calculator, and if I put 10 to the negative 7.1 in my calculator, I'm going to get 7.9 times 10 to the negative 8. All right, now, log base 10 is just written log. Log base e of x is written ln of x. This is not an I, it's ln. Okay, so these are the two ones that you need to remember the most. Now, if I have the same base here, they'll undo each other. Log base a of a, remember, it returns the exponent, so a to the x, the exponent is just the x. And the other way around, whatever, this is saying, this log would be the exponent I have to raise a to make x. Doesn't matter what that is. Let's raise a to it, we'll make x. Okay? So, the natural log of 12. I'll plug that directly into my calculator and get 2.4849. Ln of e to the 10th, well, this is log base e of e to the 10th. They'll undo each other, and I'll get just 10. Same thing here. This e would have an exponent of 1/2 because of the square root. So the natural log of e to the 1/2 would just be a 1/2. It returns the exponent. And then 12.9 to the log base 12.19 of 84. Again, same base, so these undo each other, gives me back just 84. Now, let's look and see how we got ln of 12. Your ln key's right here. So the natural log of 12 is about that value. Now notice I can also do it to evaluate some of these. Like for example, if I do that part C, ln of the square root of e to the first power, and that would be the 1/2 that we were expecting, value of the square root. All right, now some more properties. A to the 0th power is 1 whenever a is bigger than 0 and not 1. A to the kth power is going to be a to the k. And whatever value I have to raise a to make a k, if I raise a to it, I'll make a k. So these two are repeats of the previous inverse property I had on the slide. This one is new. The a to the 0 is equal to 1. Now, remember these are exponents, right? The logarithm is an exponent, so they follow the general rules of exponents. When I'm multiplying something, I add their exponents. When I'm dividing something, I subtract their exponents. And when I have a power raised to a power, I multiply those exponents. You need to know these three properties of logarithms. We can use it to rewrite an expression like this. The 5 and the x are multiplying, so I can rewrite this expression as log of 5 plus log of x. Here they're dividing, so I can rewrite this as log base 2 of 12 minus log base 2 of x. Here, I can use the property to rewrite this as an exponent first. This is log base 3 of 2x to the 1/2. Now, this property of logarithms right here tells me that I can bring the exponent down in front. So I'm going to bring down the 1/2 in front of the log, 1/2 log base 3 of 2x. Now that's 2 times x, so I can split that up with an addition. But notice this half is in front of the whole thing, so I'll put parentheses here. Log base 3 of 2 plus log base 3 of x. So that's 1/2 log base 3 of 2 plus 1/2 log base 3 of x. Now, this is log base 10 of 0.001. Now notice that's log base 10 of 1 over, that's the tens, hundreds, thousands place. Well, that's log base 10 of 1 over 10 to the 3rd. That's a -3 exponent on the 10 to make that expression. And then log base 2 of 2 to the 5th, remember, they're the same base here and here, so they undo each other. We get just the exponent 5. Now this one I can break apart, right, because I've got a division going on here. So this is log base a of the top, which is 2xy, minus the denominator, z to the 5th. Now, this is a multiplication, 2 times x times y. So I can break that, that's log base a too, into additions. Log base a of 2 plus log base a of x plus log base a of y. And then the 5 can come in front using that property of the logs. So that's 5 log base a of z. And there's our expanded expression. Let's do the same thing here. Now I'm going to start by rewriting this as an exponent. So I would have log base a. That would be m to the 2/3 power. And this division is a subtraction, log base a of n times 5. Now this 2/3 can come in front. So log base a, so we'll bring the 2/3 in front of m, minus, now this is a multiplication, so I can break it up into an addition, but this minus is in front of a log, so I gotta have parentheses. Log base a of n plus log base a of 5p plus 3. Now that's 2/3 log base a of m. This distributes minus log base a of n minus log base a of 5p plus 3. Notice that I cannot split this one up because this is not a pure multiplication. I've got an addition going in there, and I don't have a property that allows me to break up a log against an addition or subtraction. All right, now this is an exponent of 1/2, so I'm going to first write this as log base b of the whole thing, x, y cubed, z to the 9th, to the 1/2 power. Now we can bring the half down in front. Now this is a subtraction since there's a division in there. So 1/2 parentheses log base b of x minus log base b of y cubed z to the 9th. So the half distributes, and I have 1/2 log base b of x minus 1/2. This is a multiplication, so I do a parentheses, and I can break it up as an addition. So this is 1/2 log base b of x, distribute this half, minus 1/2 log base b of y cubed, so I can bring the 3 down, it would go in the numerator, and then distribute the half, so minus 1/2 log base b of z to the 9th, I can bring down and put in the numerator. And there's our simplified form. Now, we can go the other direction and build up into a single logarithm. Log base 3 of x minus, so that's going to be a division. So I would have log base 3 of x divided by y plus 2. Then plus, that's a multiplication. So multiplication goes in the top. So I'll have log base 3 of xz over y plus 2. Now here I'm going to bring up the exponents first. So this is ln of m to the 5th minus ln of n cubed. And then the subtraction means a division. So ln of m to the 5th divided by n cubed. Now, our change of base formula, log base a of x, can be written as log base anything of x divided by log base same thing of a. Now, there are really only two bases I'd want to change to, either ln or log, log, base 10, because those are the keys on my calculator. So if I want to evaluate log base 5 of 17, I'm going to write that as log of 17 over log of 5, or equivalently ln of 17 over ln of 5. Plug it into my calculator that way, and I see it's 1.76. Log base 2 of 0.1, I would write as log of 0.1 over log of 2, or ln of 0.1 over ln of 2. Plug it into a calculator either way, and I see it's negative 3.32-ish.